and welcome to Little Planet Wonder, where calm learning helps curious minds unwind. In this journey, we'll leave our small blue planet behind, travel beyond our solar system and the stars, cross galaxies and the cosmic web, and journey towards the farthest reaches of everything we can see. The universe. Step outside on a clear night and look above the rooftops, trees and sleeping streets. At first, the sky can seem almost still, a dark ceiling scattered with points of light. A few brighter than the others, perhaps the moon hanging above the horizon. But almost nothing up there is truly still. Earth is turning beneath your feet. It is traveling around the sun. The sun itself is moving through our galaxy, while the Milky Way travels through space alongside billions of other galaxies. Even as you lie completely still, you are already moving through the universe. The stars above us are not tiny lights attached to the sky. They are distant suns, separated from us by distances so immense that kilometers quickly become almost useless for describing them. Instead, astronomers often measure distance using light. Light moves faster than anything else we know, traveling nearly 300,000 kilometers every second. At that speed, it could circle Earth more than 7 times in a single second. Yet light from the sun still takes about 8 minutes to reach us. From the next nearest star, more than 4 years. And some reaching our telescopes has traveled for billions of years. And that gives us one of the strangest and most beautiful ideas in astronomy. Looking into space also means looking into the past. From here, we'll follow that light outwards, away from Earth, through our solar system, beyond the stars, past black holes and across the Milky Way, until entire galaxies become tiny pieces of a much larger pattern. Eventually, we will reach the boundary of everything we are able to see. Not necessarily the edge of the universe, only the limit of what light has had enough time to reveal. Our journey starts close to home. At its center is the sun. It looks small in our sky because it is so far away, but the sun is a star. A sphere of hot plasma more than 100 times wider than Earth. Deep inside it, tremendous pressure forces atoms together. Hydrogen is transformed into helium through nuclear fusion, releasing energy that slowly works its way towards the surface before streaming into space as light and heat. Around this star travels a family of worlds. Mercury races around closest to the sun. Venus is wrapped in a thick atmosphere and is hotter at its surface than any other planet. Earth follows, a world of oceans, continents, clouds, and life. Beyond us is Mars, cold and dusty, with towering volcanoes and valleys carved long ago. Then come the giants. Jupiter is the largest planet in our solar system, a swirling world of gas with storms larger than Earth. Saturn is surrounded by broad rings made from countless pieces of ice and rock. Uranus rotates almost on its side. Of the 8 planets, Neptune travels farthest from the Sun, taking about 165 Earth years to complete a single orbit. But the solar system contains far more than 8 planets. There are dwarf planets, hundreds of moons, rocky asteroids, icy comets, dust, and countless smaller objects traveling along paths shaped by gravity. Together, they form our local neighborhood in space. Yet even this neighborhood is difficult to picture. If the Sun were reduced to the size of a grapefruit, Earth would be little more than a tiny speck several meters away. Neptune would be hundreds of meters farther out, followed by an immense stretch of almost empty space before reaching another star. The solar system can feel huge when viewed from Earth. On the scale of the universe, it is barely a beginning. Leave the planets behind and the stars take over. Every star has a story. Many are born inside immense clouds of gas and dust. Gravity slowly pulls material together. Regions of the cloud become denser, collapse inward, and grow hotter. Eventually, conditions at the center become extreme enough for nuclear fusion. A star is born. For much of its life, a star exists in a kind of balance. Gravity pulls its material inward, while energy produced within pushes outward. Depending on its size, that balance can keep a star shining for billions of years. But stars are not all alike. Some are smaller and cooler than our Sun. Others are hotter, brighter, and far more massive. Their colors reveal something about their temperatures. Cooler stars can appear reddish, while hotter stars shine blue-white. And their size helps determine how their lives will end. A star similar to our Sun eventually exhausts the hydrogen fuel in its center. Its outer layers expand, turning it into a red giant. Much later, those outer layers drift away, leaving behind a small, hot remnant called a white dwarf. More massive stars have a far more dramatic ending. They burn through their fuel quickly. Their centers eventually collapse and their outer layers can explode outward in a supernova. For a few brief weeks, a single dying star can outshine its entire home galaxy. The explosion scatters material into space. Carbon, oxygen, iron, and many other elements forged inside stars or during their deaths can become part of new clouds, new stars, and new planets. The calcium in bones, the iron carried through blood, the oxygen we breathe. Much of the material that makes worlds and living things was once processed inside stars. Stars are more than lights above Earth. They are part of the story of how our planet came to exist at all. For some massive stars, even a supernova is not the end. After the explosion, the remaining core can continue collapsing. matter is compressed into an extraordinarily compact region. Gravity becomes so strong that a black hole forms. A black hole is not a giant hole punched through space. It is a region where gravity has become extreme. Around it lies a boundary called the event horizon. Cross that boundary, and escaping would require traveling faster than light. As far as modern physics tells us, nothing can do that. Not matter, not spacecraft, not even light itself. That is why black holes are black. We cannot see a black hole directly, but we can detect what it does to its surroundings. Gas falling towards one can whirl into a hot disk, producing intense radiation before crossing the event horizon. Stars can orbit an object that appears invisible, and when black holes collide, they can send ripples called gravitational waves across the universe. There are black holes only a few times more massive than our Sun, and supermassive ones containing millions or billions of times the Sun's mass. One of these sits at the center of our own galaxy. Black holes can sound like cosmic vacuum cleaners, but they do not roam through space swallowing everything nearby. From far enough away, their gravity behaves like that of any other object with the same mass. If the Sun could somehow be replaced by a black hole of exactly the same mass, Earth would become dark and frozen. But it would continue traveling around it along almost the same orbit. Black holes are extreme, but they still obey the deeper rules shaping the cosmos. Draw back further still. The Sun shrinks into the background. Other stars appear around it. Hundreds become thousands. Thousands become millions. Eventually, a new shape emerges. A galaxy. Our galaxy is the Milky Way, a vast collection of stars, gas, dust, planets and dark matter held together by gravity. From inside it, we see part of its structure as a pale band stretching across a dark night sky. But if we could travel high above the Milky Way and look back, we would see a very different picture. A broad disk, a bright central region, and sweeping spiral arms curving through the galaxy. Our Sun is only one star among hundreds of billions. It lies well away from the galactic center, in a smaller structure known as the Orion Spur. One journey around the center of the Milky Way takes the Sun roughly 230 million years. The last time our solar system was in approximately this part of its galactic orbit, dinosaurs had not yet appeared. At the center of the Milky Way lies the supermassive black hole, Sagittarius A. Around it, stars race through crowded regions of the galaxy. Farther out, they become more widely separated. Beyond the bright disk extends a much larger halo containing old stars, clusters, and large amounts of unseen matter. From Earth, the Milky Way can seem like the universe itself. For most of human history, nobody knew that other galaxies existed beyond it. Then, telescopes reached deeper into the night, and faint smudges of light revealed what they really were. The Milky Way was not everything. It was one galaxy among billions. Now even the Milky Way starts to shrink. Its spiral arms blur together, and nearby, another large galaxy comes into view. Andromeda. Smaller galaxies appear next, then more. Across the observable universe, galaxies come in many shapes and sizes. Some are spirals like the Milky Way, some are smooth, rounded ellipticals. Others have irregular forms, shaped by gravity, collisions, or their own complicated histories. Galaxies can pass near one another, pull streams of stars and gas across space, collide, and over immense periods of time, merge. The Milky Way and Andromeda are themselves moving towards one another and are expected to interact billions of years from now. But a collision between galaxies is unlike two solid objects crashing together. Stars are separated by so much space that most are unlikely to strike another star directly. Instead, gravity reshapes the galaxies. Orbits shift. Gas clouds collide, stars can be born, and two galaxies can gradually become one. Widen the view again. Our Milky Way and Andromeda belong to a collection called the Local Group, alongside dozens of smaller galaxies. The Local Group is itself part of a much larger cosmic landscape, and here, another pattern appears. Galaxies are not scattered evenly through space. They gather. At this scale, the universe begins to resemble a web. Galaxies gather into groups, groups into clusters, while clusters connect through immense filaments stretching across space. Between them lie regions containing far fewer galaxies. These are cosmic voids. Together, the filaments, clusters, and voids form what astronomers call the cosmic web, one of the largest patterns we know. A single galaxy is now almost too small to notice. Even the Milky Way, with its hundreds of billions of stars, becomes little more than a point inside this enormous structure. How did such a pattern form? The early universe was extremely smooth, but not perfectly so. Some regions contained slightly more matter than others. Gravity amplified those tiny differences, and regions with more matter attracted still more. Across billions of years, matter gathered into increasingly complex structures. Stars formed, galaxies grew, clusters assembled, and the web emerged. But there is a problem. When astronomers study the movement of galaxies and the way gravity shapes the cosmos, the matter we can see does not appear to be enough. An invisible influence seems to be helping hold this structure together. Consider everything we have encountered so far. Planets, stars, gas, dust, galaxies. All of it is made from ordinary matter. The same basic kind of matter that makes oceans, rocks, trees, and people. Yet, ordinary matter appears to make up only a fraction of the universe. Most of the cosmos seems to consist of things we cannot directly see. The first is dark matter. Dark matter does not appear to produce, absorb, or reflect light in the usual way. We know about it mainly through its gravity. Galaxies rotate as though they contain far more mass than we can see. Light from distant objects bends around massive regions of space more strongly than visible matter alone can explain. And the cosmic web has grown in ways that point towards additional, unseen mass. We call it dark matter because we know remarkably little about what it actually is. There is an even deeper mystery. In the late 1990s, astronomers studying distant exploding stars discovered that the expansion of the universe was not slowing as many had expected. It was speeding up. Whatever drives that acceleration has been given a name: dark energy. The name is useful, but it is not an explanation. Our best measurements suggest that ordinary matter, everything from people and planets to stars and galaxies, makes up only about 5% of the universe. Dark matter accounts for roughly another quarter, while most of the remainder is attributed to dark energy. Everything we have ever touched, every planet we have discovered, every star shining in every galaxy, belongs to that narrow, visible portion. Most of the universe remains hidden from us. There is another way to travel through the cosmos, not only across distance, but backwards through time. Look at the moon, and you see it as it was a little over 1 second ago. Look at the sun, and you see light that left its surface about 8 minutes earlier. Look at the nearest stars, and you see them years in the past. Look at Andromeda, and the light entering your eyes began its journey roughly 2.5 million years ago. This happens because light has a speed limit. The farther away an object is, the longer its light needs to reach us. So when astronomers build telescopes capable of seeing deeper into space, they are also building machines that reveal earlier chapters of cosmic history. Some galaxies seen by our most powerful telescopes appear as they were more than 13 billion years ago. We see them when the universe was young. Their light has been traveling towards us across expanding space for almost the entire history of the cosmos. Go back far enough, and eventually there are no stars, no galaxies. The universe was hotter, denser, and simpler. About 380,000 years after the Big Bang, the universe cooled enough for light to travel freely through space. That ancient light still fills the universe around us today. It is called the cosmic microwave background. We cannot see anything earlier using ordinary light, because before that time the universe was filled with hot material through which light could not travel freely. It is as though we have reached a glowing wall in the deep past. Beyond it lies the universe's earliest history. We have now traveled almost as far as light can take us. And here we encounter an important boundary: the observable universe. The universe is about 13.8 billion years old. It might therefore seem reasonable to imagine that we can see 13.8 billion light-years in every direction. But space itself has been expanding while the light traveled. Because of that expansion, many of the regions whose ancient light reaches us today are now much farther away. The present-day radius of the observable universe is roughly 46 billion light-years. From one side to the other, it is therefore around 93 billion light-years across. Within it are countless galaxies. Within those galaxies, countless stars. And around many of those stars, planets. Yet the observable universe is not a sphere with Earth sitting at the special center of everything. It is simply the region from which light has had enough time to reach us. An observer in a distant galaxy would have their own observable universe centered upon them. Our cosmic horizon is created by time, distance, and the expansion of space. Beyond it may lie more galaxies, more stars, more planets, perhaps far more than we can observe. Their light simply has not reached us. And some regions are now so distant that because cosmic expansion is accelerating, light emitted there today may never reach us at all. There are parts of the universe that may remain permanently beyond our view. So what lies beyond the observable universe? The most accurate answer is also the simplest. We do not know. The observable universe may be one region within a much larger whole. The wider cosmos could extend far beyond our horizon. It may even be infinite. Scientists can study the geometry of space, test cosmological models, and search for clues in ancient light. But observations can only take us so far. That distinction matters. The edge of the observable universe is not necessarily a physical edge. There is no known wall, no final row of galaxies. No place where a spacecraft would reach the end of space and find nothing beyond it. It is a horizon. Like standing beside an ocean and seeing only as far as Earth's curve allows. The ocean continues beyond your view. Reality may extend far beyond everything our telescopes can currently observe. Future discoveries could reveal new ways of understanding it, while some questions may remain unanswered. The universe has repeatedly done this to us. Each time we thought we understood its scale, another layer appeared. Earth was not the center of the solar system. The solar system was not the center of the Milky Way. The Milky Way was not the entire universe. And the observable universe may not be the whole universe either. Every answer has widened the view. Now begin the journey home. The cosmic horizon falls behind us. The web of galaxies grows larger. Clusters separate into individual galaxies. One spiral becomes familiar, the Milky Way. Move towards one quiet region of one spiral arm. Billions of stars pass by. One becomes brighter, the Sun. Around it, 8 planets follow their paths. Past Neptune, past Uranus and Saturn, past Jupiter, past Mars, until a blue world appears in the darkness. Earth. From here, there are no visible borders between countries. No cities bright enough to change the shape of the planet. Just a thin atmosphere, white clouds, blue oceans, land, and darkness beyond. Everything humans have ever discovered about the universe began here, with people looking up. We built instruments to collect faint light, learned that Earth travels around a star, discovered that the stars are other suns, and found galaxies beyond our own. We detected invisible matter through its gravity, measured ripples in space created by colliding black holes, and built telescopes capable of receiving light that began traveling towards us billions of years before Earth existed. Yet, the farther we have looked, the more clearly we have seen how much remains unknown. We still do not know what dark matter is. We do not understand the true nature of dark energy. We do not know what lies beyond our observable horizon, or whether life exists somewhere else among the stars. And perhaps that is one of the most important things the universe can teach us. Discovery does not make the mystery disappear. Sometimes, it makes the mystery larger. Tonight, the stars above you may look exactly as they did before, points of light scattered across a dark sky. But what you see has changed. Stars being born inside clouds of gas, planets circling distant suns, black holes bending space, galaxies turning slowly through the darkness, filaments stretching across the cosmos. Ancient light carrying messages from a universe billions of years younger than it is today. And somewhere within all of it, one galaxy, one star, one blue planet, and us, still looking up. If this journey sparked wonder, we'd love to have you with us on future journeys. Thanks for listening, and for exploring these moments with Little Planet Wonder. Until next time, stay curious and keep exploring.